you can see our objectives for today. We're going to define what it means to take a measurement. We're going to learn about the SI system, about different units, and then we're going to learn to convert between them. Then we're going to talk about significant figures. There's not a section in the notes where we fill out notes about significant figures, but I will have the same material handout from chemistry last year that has all of the rules on it that I will put in the materials section of Classroom for you. And then we will go through ways to identify errors in data sets. Okay. Those are our sort of goals. So we'll start with what is a measurement, because if you ask someone what a measurement is, oftentimes they will just give you a number. However, if I simply wrote the number 2 down on a piece of paper and gave it to you, that would not qualify as a measurement. In order for something to be a measurement, you must have both, one, a specific quantity that you are measuring. So am I measuring the length of an object? Am I measuring the mass of an object? Am I measuring how long it takes an object to move from point A to point B? What is it that I am measuring? So quantity. And then I must also have a unit of measurement, whether that be a meter or an inch or grams or kilograms, pounds, seconds. Newtons is one we're going to use a lot this year. So we have to know what unit we were measuring in. Okay. The first part, the quantity, tells the person what you're measuring, and then the number gives them a value, but the unit makes sense of that numerical value, because 2 inches and 2 centimeters are very different things.
Wouldn't the unit of measurement tell you what it was, what the quantity would be?
Yes. So most of the time, you are not going to have to write, I am measuring this in time, because having a unit tagged on the end of it tells us what quantity we're measuring.
But you can't just put Z as a unit of measurement.
Right. Exactly. And if you were using a measurement that not a lot of people are familiar with, you might indicate what you are measuring. So, for example, for the first couple of times that I introduced newtons to my freshman class, I always say newtons are unit of force, because they forget what a newton is measuring. Oh. And we are going to talk about this a little bit later, but it is good, even if you don't write it down, it's good that you know what you're trying to measure, because if your quantity and your unit don't match up, that can be a good indication to you that you may have done a calculation incorrectly.
Like you can't really have negative distance.
Right. Yep. And sometimes you'll find in physics we're going to do these long, complicated problems, and we wind up with derived units, which we'll talk about here in a second. So it's like a combination of multiple units. And if you know what unit you're supposed to or you know what quantity and what unit you're supposed to end up with, and you don't end up with that unit, then you probably did some math incorrectly somewhere in the middle. Which is why I will also ask you to very kindly, I know it is extra work, but when you do your homework, you will thank yourself if you use the units all the way through the math and not just tag them on at the end.
What?
Yeah. Because that way you can catch an incorrect unit, whereas if you just slap it on at the end, you might miss that you divided something wrong in the middle and wound up with the wrong unit. Units didn't cancel, stuff like that. So keeping those units on there is going to be especially important this year.
I started doing that when we were converting like grams and moles and all that jazz.
Yeah, it's just one of those little bugger of a things, but I cannot tell you how many times I have caught a mistake that some of my classmates missed because I kept all my units in there. And I don't consider myself particularly great at math. I am capable, but it takes me a long time and it's difficult for me. But I would consistently come up with the right answers simply by following the units. In fact, sometimes even if you don't know how to do the math, you can figure it out based on the unit you're supposed to end up with, which is awesome. It's a great feeling. Okay, in science, we're going to use the SI system because it's recognized universally across all of the nations. It shares a lot in common with the metric system, but it does have some pieces that are not metric in it, particularly as we move to temperature and things like that. But for the most part, it's very similar to the metric system. There are base units of measurement for SI. These are your sort of common base units. Time is going to be measured in seconds. Length is going to be measured in meters. And mass is going to be measured in kilograms. In chemistry, we used a lot of grams because we calculated things in small amounts. Physics tends to deal more, at least in the first unit, on the large scale, so you will probably see kilograms more this year. And then we have some units that can't be measured using a base unit, and this is what we call a derived unit. We derive it by multiplying or dividing base units. So for example, speed is a derived unit. Because speed is a measure of a distance in a unit of time, we can't just measure it in time or distance. We have to have both, so it's measured in meters per second. Or force, which is newtons, one we're going to come across a lot. Newton is the simplification of it, but it really means kilograms times meters per second squared. The mass times the acceleration. So when we measure very large objects or very small objects, we're going to use scientific notation, hopefully familiar to you. I know we did it some last year. So this is just converting to a decimal. So where you have one number on the left of the decimal and a couple of numbers on the right of the decimal, and then you have times 10 to an exponential power to help you convert it. So a million would become 1 times 10 to the 6th, or 0.00000000, however many zeros that is. 1 becomes 1 times 10 to the negative 9. So the positive or negative value on the exponent tells you which direction to move the decimal when you are putting it back into its normal form. And then, of course, we always have the great fun if you are multiplying numbers in scientific notation, you add the exponents, and if you are dividing numbers in scientific notation, you subtract the exponents. So, good things to remember. I'm moving through this pretty quickly, assuming it's something you have done before, but if we get to practice and you're having trouble with it, of course, you can ask me for assistance on it. I'm more than willing to help.
We should be pretty good because everyone else would keep it in decimal for as long as they could before scientific notation, even if it was like 0.0003. But even when it was 0.003, I would turn it to scientific notation.
Good. And oftentimes, especially as we deal with these huge numbers, the only way to get it to the correct number of significant figures will be to put it into scientific notation, so it is a necessary skill. All right, now we're coming to this table. You have the powers and the abbreviations, so you just need the prefixes. And again, just like last year, I'm not going to expect you to memorize this. On most tests, you will get a full sheet that has all of these on it. We very rarely, I would say, go above sort of mega in terms. So if we're starting at the base unit, deca is 10 to the first, then kilo 10 to the third, mega 10 to the sixth. We don't tend to use the prefixes much past that, but you may occasionally run into one in a problem in your text, so I want you to have this resource available to you.
Are the abbreviations for kilo, deca, and mega?
So that's a good question. Okay, so the prefixes are sometimes something we can use instead. So instead of saying, instead of writing out 1,000 grams, I can write a 1 kilogram.
I was looking at 10 to the third. It was like 10 to the third is a kilo, but it's 1,000. That's a kilo.
Yes.
And 10,000. Okay. We
Yep.
did go over this. Just it was 1,000, 100.
Yes.
10,000. Okay. We're good now.
Yep. It's just written out to the power to simplify the number of zeros I have to write over there. And then on the opposite end of things, as we go lower, I would say we probably tend to use deci, centi, and milli, sometimes occasionally micro, but not a lot below that. Micro is that fun, tricky one that's got the Greek letter for its symbol, because we had too many M's already. So.
Can we go back onto the big words?
Uh-huh. Building equivalencies helps to convert between units. So 1,000 meters over 1 kilometer, or 1 kilometer over 1,000 meters. Those would be equivalencies. We use these a lot in chemistry. I wish it was easier to draw them actually over each other on Word, but it's a little tricky. So when you're converting 4 kilometers to meters, you would simply pick the correct equivalent. So you would want, in this case, kilometers to be on the bottom so that the units would cancel. And you'd wind up with 4 kilometers times 1,000 kilometers over 1 kilometer, which would translate to 4,000 meters, because those kilometer units would cancel. If your units don't cancel, then you used the wrong equivalency and you need to pick the other one. Before doing math, make sure your measurements match both in dimension and units. So if you're trying to convert and you're trying to convert from seconds to meters, that's not going to work. So you need to make sure you're using the same measurement and unit to convert. To practice, we have a little practice problem. Okay, so a scanning tunneling microscope, or STM, has a magnifying ability of 100 million. They're pretty impressive. And they can distinguish between two objects that are separated by only 3.0 times 10 to the negative 10 meters, or about 1/100th of the diameter of an atom. Pretty crazy impressive microscopes, okay? What I would like for you to do is to express 3.0 times 10 to the negative 10 meters in both nanometers and picometers. So I will set myself a little timer for about 5 minutes, and then we'll go over this. Okay. We'll start with the nanometers. So we have to start by giving ourselves the correct equivalencies, the correct conversion factors, if you will. You can use both word. So the conversion factors we could use is that for every 1 nanometer, we know that it is 1 times 10 to the negative 9 meters, right? We can tell that from the chart. You following?
So I can just... So nanometers and meters.
Mm-hmm.
How do we, I see 10 to the negative 9 is 5 nanometers.
Yep.
How do we,
That
so
is compared to the base unit. So one nanometer would be 10 to the negative 9 meters. Or vice versa. Yes.
Okay. Okay.
Yep. So whatever your base unit is, if you those prefixes is compared to the base unit.
I put an M, and whatever 10 to the negative 3 is word-wise, I don't have to like fill in. I was trying to figure out how 10 to the negative 3 and the 10 to the negative 9 are supposed to relate to each other, and I was
Nope.
just kind of staring at it. Okay.
Nope.
I think we're good.
Okay.
I can continue from here, knowing that those are...
Got it from here? Okay. So if we're using this and we're starting with, 3.0 times 10 to the negative 10 meters, we're going to take it times 1 nanometer, keep writing M instead of N, times 1 to the negative 9 meters. Meters cancel. We can subtract negative 9 from this because we're dividing. So it's like adding. So we should wind up with 3.0 times 10 to the negative 1 nanometers. Or if you wanted, you could move that decimal point over here and put 0.30. Either way would be correct. And let me wipe my screen. Then if we're doing picometers, then we still start with the 3.0 times 10 to the negative 10 meters, but our conversion factor this time will be 1 picometer is actually 1 times 10 to the negative 12 meters. And then you again cancel meters, and again you subtract negative 12, so you wind up adding. So what you should wind up is 3.0 times 10 to the 2 picometers. And in this case, you have to leave it in scientific notation because we have 2 sig figs, and if you carried this out, you would wind up with more significant figures than that. So we have to leave it in scientific notation for this one. Questions about this? It gets a little bit more confusing when you are converting between 2 units that are not base units. So if you get stuck on a problem like that, we can work one out.
Like I thought we were doing.
Yes. Okay. Let's talk accuracy versus precision. We talked about this last year, so it should be very familiar. When we talk in everyday conversation, people use the word accurate and the word precise to mean the same thing, but they are not really the same thing in everyday life, even though people use them that way. But especially in science, they have different meanings. Accuracy has to do with how close a measurement is to the correct or to the accepted value for something. And it's limited by either you making an error or you not having a skill with using a certain apparatus. So that can cause errors in your accuracy. Precision, on the other hand, is the degree of exactness of a measurement. So basically, the more decimal points you can add to your number, the more precise you can be. How close can you measure it? Can you only measure it to how many meters, or can you measure it to centimeters or decimeters? As a result, this one is not due to skill, but it's actually limited by your measuring devices. Okay, so if we had that scanning, tunneling microscope, okay, we would have a much greater precision on our small measurements of small objects than if we had the microscopes that I have in my room today and we're looking at small objects and trying to measure them. Another way of thinking about this is precision is how close your measurements are to each other. So if you have very precise tools, you will be able to get measurements that are very close to each other, whereas if your tools are less precise, then your measurements may vary a little bit more. And then accuracy is how close to the correct value you got. So a lot of times you will see people use the target diagrams that show different groupings, which we'll look at here in just a second. So I gave you an example here. Some measuring devices can measure 1.325. Some are only capable of measuring to 1.3, which would be less precise. And this is the reason why we have to have significant figures, is because if you only have a device that can measure to 1.3, you can't report those last two digits because you weren't actually capable of measuring them. So you can only report the first two. Even if other measurements in your data set go out further, you're limited by the precision of the first one. So the first target here is showing you both high accuracy, they've hit the bullseye, that's the accepted correct mark, and high precision. It is a very tight grouping because their tools are very precise. So you could say they had a very precise sight on their bow, right? Was able to very accurately tell them the position of that target. Then in the second target, we have low accuracy. So they did hit the mark, but high precision. All of their arrows again hit in a tight grouping, meaning they were able to dial in their target. They just didn't have the skill to hit the bullseye. And then in the third one, we have high accuracy. They're relatively close to that accepted mark, but low precision. They're a little bit all over the place. And then finally, on the last one, the one we would like to avoid in scientific research is both low accuracy and low precision, where you're kind of all over the place and you're not hitting the mark. All right, the last thing we need to talk about is error analysis. Okay, we are human. It is impossible that we will not make errors in our data. However, there are some things we can do to limit the amount of mistakes or identify mistakes when we do have them in our data, so we don't come to incorrect conclusions based on mistakes in the data. The first thing you can do is, before you even begin your experiment, plan to do multiple trials. We did this yesterday, in fact, when we were doing the monkey versus the hunter experiment. We didn't just fire once and then assume that that was correct. We did multiple trials to verify things. So more trials is always better in science if you can do it. And if you can't do more trials, a larger sample size would suffice as well. So more test subjects, okay? We want a large pool of data from which to draw conclusions. The more data it is, the more outliers from errors stand out. Okay? If you only have 10 trials, you might not notice that 2 of them are way outside the mark. But if you have 100 trials and 2 of them stick out, you can tell that maybe there was an error there that caused those 2. Okay? Next up, we can describe data using different tools that help us avoid those errors. So tools like mean, median, and mode. You've probably been using these in math since like 5th, 6th grade. Okay? Mean is your average, so taking an average of a group of data, again, helps us to averaging things in helps us to, again, avoid those outliers, counting too much. Without a mean, you can't find your standard deviation. which is a tool. Standard deviation is a tool that allows us to find outliers, so having a mean is helpful for that purpose. Median gives you what the middle point of your data is, which is just often very useful.
Today's announcement.
And mode tells you which data is coming up most often, which is a nice indication of how precise you were with your measurements. So if your mode is reflected in or very similar to a lot of your data, then you probably were very precise with your measurements. Are you okay?
Yep.
Okay. Standard deviation. When you calculate your standard deviation, you're comparing all of your data points to your average. This makes it easier to spot outliers. Okay, so if things are really far away from your average, then you probably should exclude them from your data set. And then finally, percent error is something that we're going to use. Percent error you've done in chemistry. It's your experimental value minus your accepted value divided by the accepted value and then times 100 to turn it into a percentage. Percent error gives you an indication of your accuracy. Of course, not every experiment can have a percent error because not every experiment has a accepted value, but when you have an accepted value, then you can compare it to your accepted value, and your percent accuracy or percent error will tell you if you were over or under or very close to your accepted value. If it's negative, then your value is less than accepted. If it's a positive value, then your value is greater than the accepted value. All right, that is the end of the notes for today.